Lambert for the introduction. So my name is Abdulqader, and this is already, I think, the fourth time I'm here. So I'm very happy to be back talking to all of you wonderful students out here. So today's topic will be about the bioeconomy. So this is a very rapidly evolving field. So, for example, as a chemical engineer, this is particularly relevant to us because it merges the principles of biology with the processes and technologies we are familiar with to create sustainable solutions across the various industries. So the bioeconomy leverages biological resources such as plants, animals, and microorganisms to produce energy, materials, and chemicals in a way that reduces our reliance on fossil fuels and also mitigates environmental impact. So throughout this lecture, we'll explore what is the bioeconomy and concepts such as the circular economy and why is it relevant to us. So without further ado, let's begin. So here's an overview of what we'll cover in today's lecture. So we'll start with an introduction to the concept of the bioeconomy. Next, we'll dive into bio-based products. So those are the materials, chemicals, and fuels derived from biological resources. We'll then move on to discuss the bio-based methods, which include the technologies and processes that drive the bioeconomy forward. After covering the main content, we'll wrap up with a conclusion that ties everything together, followed by a quick exercise to help us apply what we have discussed. Finally, we'll end with a Q&A session where I'll be more than happy to answer any questions that you may have. All right, so without further ado, let's begin with the introduction. So to begin this lecture, I would like to share a quick video about the bioeconomy, which I think will be very helpful. So please, Dr. Lambert, do confirm if you can hear what is happening right now. So I'm starting to the video.
Abdulqader, are you talking? Because we do not hear you.
I am currently sharing the video. Could you hear the audio or?
Oh no,
is it?
that's what it is.
Ah,
When you share the video,
yeah.
there's a little button down at the bottom left that says include computer audio or something like
Audio.
that. So you need
Okay.
so before you share it, you have to click on that button.
Okay, let me try again. Sorry for
Yeah.
that. All right, let me try again. I'll stop sharing and I will share with okay, share sound. All right, I've seen the option.
There
Now.
it is.
All right, perfect. Thank you for that. All right, so maybe we can just go ahead. So I was just saying that I would like to show this quick video as an introduction to the concept of bioeconomy, which I think will be very helpful throughout the lecture. So I'm going to start. So now
what
can
do
you
we
hear the
mean
audio?
when we talk about
Good,
the
we can hear it now.
bioeconomy?
Perfect.
To break it down, the term bio refers to any living thing, while economy means the making and usage of goods and services by those within a country or region. So the bioeconomy is an economy based on renewable biological resources. These resources may be converted into food, feed, bio-based products, or bioenergy. There are three key areas to the bioeconomy: growing bio-based resources, turning these resources into bio-based products and services, and using bio-based waste to make new products or services. Let's start by looking at growing bio-based resources. This could include crops, including cereal crops like maize, corn, barley, but also fungi, seaweed and algae, or animals, farm animals and fish, but also bees and worms, or microorganisms like bacteria and yeasts, and even cells, both human and animal. Next is turning these resources into bio-based products and services. This could include food products for human or animal consumption, byproducts from food production for plastics or fuel, energy via bio-oils, chemical products derived from plant sources, algae or microbes to clean water supplies instead of chemicals. And lastly, we can use bio-based waste to make new products or services. Food waste can be used to create energy to power our homes and businesses. Agricultural waste can be processed into sugars for use in making medicine. And even empty pea pods can be used to make tiny carbon particles for use in electronics. A bioresource can appear in any or all of the three key parts of the bioeconomy. For example, a cereal crop like barley can be used as animal feed or processed to make alcoholic drinks. The straw that is left behind after the barley harvest can be used to generate energy. Algae and seaweed can be used as animal feed in an untreated state. Once processed into extracts like agar, carrageenan, and alginate, they become important ingredients in foods, cosmetics, and medicines. The waste materials left behind after seaweed processing can be used in anaerobic digesters to create biomethane for energy. Whether it's food, fuel, or energy, they can all be produced using renewable, bio-based products. The potential for growth in all these areas means a growth in potential career options. The bioeconomy includes multiple industries, so the job opportunities are diverse. These roles and many more are all found in the bioeconomy. By 2050, nearly 10 billion humans will live on Earth. They will consume 40% more energy and 50% more food. For the health and the wealth of our society, we need to move away from fossil fuels and live sustainably. A replacement for many oil-based products can be found within the bioeconomy by making more use of bio-based resources and by moving away from a take, make, use, discard model to a take, make, use, recycle approach. Our way of life will be sustainable for the planet, for us, and for future generations. The bioeconomy is the future economy.
All right, so that was just a very quick video to give you an introduction to the bioeconomy. So we've seen from this video, and we'll just revise on the concept. So what is the bioeconomy? So the bioeconomy is a comprehensive concept that encompasses the production of renewable biological resources and their conversion into valuable products, such as food, feed, bio-based products, and even bioenergy. So this is achieved through innovative and efficient technologies that maximize the use of biological materials. For us as chemical engineers, the bioeconomy is particularly significant because it involves transforming raw biological feedstocks, such as those derived from agriculture, forestry, and even side streams from food production, into useful and sustainable products. So as I mentioned, the feedstock comes from already bio-based resources. So from agriculture, even waste streams. So all of these can be used in the bioeconomy. And then we also talked about the circular economy, as it's very closely related. So what is the circular economy? Well, the circular economy is an industrial system that is designed to be restorative or regenerative by intent. So what does this mean is basically, unlike the traditional linear economy, which follows a take, make, dispose model, as we saw in the video, the circular economy seeks to replace the end-of-life concept with restoration and regeneration. What this means is that in this system, we shift towards using renewable energy sources, eliminating the use of toxic chemicals that impede the reuse and recycling of materials. The circular economy also focuses on the elimination of waste through better design, whether it's materials, products, or entire systems, and by rethinking business models to support sustainability and resource efficiency. So in the European Union, several key areas have been identified as priorities for advancing the circular economy. These represent sectors where significant impact can be made through circular practices. So first, we have food waste. So how does this apply? So by reducing food waste, this is a very important priority, as not only it conserves resources, but also reduces greenhouse gas emissions associated with the waste disposal. Then we have the biomass and bio-based products. So the EU emphasizes the importance of using the biomass and developing bio-based products to replace the current fossil-based materials. So this aligns with the sustainability goals. Then we have plastics. So the focus here is on reducing plastic waste, promoting recycling, and also developing alternatives that are less harmful to the environment. Then we have critical raw materials. So this is to ensure that there is sustainable supply and efficient use of raw materials that are critical to the economy, including and through recycling and substitution. And finally, we have construction and demolition waste. So we have to address the waste generated from construction and demolition, as this is very important, as this sector is a significant contributor to the total waste of production, especially in the EU. So these priority areas give us policies and innovation efforts to build a more sustainable and resilient economy. So what is the role of the bioeconomy in the circular economy? Well, the bioeconomy is circular by nature. What this means is that it is circular in nature as it revolves around using renewable biological resources and recycling them back into the economy. Not only that, but the bioeconomy regenerates carbon dioxide and utilizes renewable raw material to more sustainable products. The bio-based products and materials tend to achieve a more balanced carbon cycle compared to fossil alternatives. They are less carbon intensive, making them actually more environmentally friendly. Not only that, is that the circular economy should facilitate the recycling of carbon after its efficient use. So this complements the bioeconomy by ensuring that the carbon is reused and regenerated rather than just being released into the atmosphere as waste. Now we will move on to talk about the bio-based products. So this slide provides two definitions of bio-based products from two authoritative sources. So one from the US and one from the EU. So the United States Department of Agriculture, or USDA for short, they say that bio-based products are commercial or industrial products other than food or feed that are composed in whole or in significant part of biological products or renewable domestic agricultural materials. So these can include plant, animal, and marine materials, as well as forestry materials. As for the EU, the European Commission defines bio-based products as non-food products derived from biomass, which includes plants, algae, bacteria, crops, trees, marine organisms, and biological waste from households, animals, and food production. So these products can range from high-value fine chemicals, such as pharmaceuticals and cosmetics, to high-volume materials, such as general biopolymers or chemical feedstocks. So these definitions highlight the broad range of materials and applications that fall under the umbrella of bio-based products, reflecting their importance in various sectors and their role in driving the bioeconomy forward. Moreover, this slide further clarifies the term bio and bioproducts, emphasizing that it refers to the inputs derived from biological sources. So as we say, these include agriculture, food processing, forestry. So understanding these sources is crucial because it highlights the diversity of raw materials that can be actually utilized in creating bio-based products, ensuring that we make the most of our natural resources in a sustainable manner. So bio-based products can be broadly classified into three main categories, each serving distinct functions and markets. So first we have bioenergy. So this includes liquid fuels like ethanol and biodiesel, which are used for transportation, as well as solid biomass that can be combusted to produce heat and power. Additionally, gaseous fuels such as biogas and syngas are included, both of which can be used for generating heat and power. Then we have biomaterials. So this category covers a range of materials such as bioplastics made from plant oils and sugars, biofoams, biorubber derived from plant oils and latex. It also includes biocomposites, which are created from agricultural biofibers like hemp, flax, kenaf, and so on. We also have forestry biofibers, which are used in products such as automobile door panels and parts, so in our cars. Then we have biochemicals. These are industrial chemicals and resins, including paints, lubricants, and solvent. So this category also covers pharmaceuticals, such as antibodies and vaccines produced by genetically modified plants and natural medicine compounds. Additionally, this includes biocosmetics, including soaps, body creams, and lotions falling under this classification. So the goal is that I want to highlight these classifications because this shows the diverse applications of bio-based products, demonstrating their potential to actually replace the traditional fossil-based products across various industries. First, let's start talking about ethanol or bioethanol. So ethanol and biodiesel are actually the most common biofuels that are currently used, and they are serving as potential alternatives to traditional fossil fuels. These biofuels are typically blended with petroleum-based fuels like gasoline or diesel. So if you go to your gas station, you probably have seen that they already have, for example, blended petroleum diesel, so with 10% biodiesel or 7% bioethanol, for example. So this blending is common in the transportation sector to reduce the greenhouse gas emissions and also the reliance on the pure fossil fuels. Currently, research is being conducted to produce ethanol directly from non-food sources like cellulose or syngas. However, this innovation could significantly broaden the range of feedstocks used for ethanol production. However, it's important to note that producing ethanol from cellulose is currently more expensive than traditional grain-based methods, which poses a challenge for scaling up this technology. So in response, many companies are investing in research to optimize the process of breaking down the cellulose into fermentable sugars. Their goal is to reduce production costs and increase the efficiency of ethanol yields. Despite the challenges, there are significant interest in these new technologies, and their potential to utilize a wide range of biomass feedstock will make them a more attractive option for the future of sustainable energy. Then we have biodiesel. So let's talk about biodiesel. So biodiesel is produced through a chemical process called transesterification, where vegetable oils, fats, and greases are converted into biodiesel. So common oilseed crops are like soybean and canola, which are frequently used in the production of biodiesel. These crops are a renewable source of oil that can be transformed into fuel. In addition to the fresh crops, we can also use recycled vegetable oils from restaurants and animal fats, which can be further processed into biodiesel. So this makes it a sustainable way to reuse waste products. So instead of just throwing out the waste cooking oil, it can actually be sent and processed to make biodiesel, which is a very useful product. There's also microalgae, which is another promising source for biodiesel. These organisms produce substantial amount of oil, and research is ongoing to harness their potential for fuel production. So, however, it is still not commercial, the use of microalgae, so research is ongoing to scale up algae production to an industrial level. Then we have bio oil or pyrolysis oil. I'm sure you've heard of pyrolysis oil in a previous lecture. So bio oil, just to give a quick revision, pyrolysis oil is produced through a process called pyrolysis, which basically involves the rapid thermal decomposition of organic materials, such as wood and agricultural biomass, in the absence of oxygen. This could also include even plastic waste as a potential source for the pyro oil. However, the quality of the resulting bio oil can significantly depend on the type of biomass used in the process. So if you've used plastic, for example, the quality of the bio oil or the pyrolysis oil is going to be significantly different than if we have used biomass, for example. So high quality bio oil is characterized by its low water content. So that's how we know when it's very good quality, because it can be used as a substitute for the additional fuels like diesel, heavy fuel oil, light fuel oil, or even natural gas, making it a versatile energy source. In addition to being used as the fuel, some bio oils contain high value chemicals that have significant industrial or medical applications. So this even adds further to the economic value of the pyrolysis oil. Then we move on to biogas. So biogas is produced through a process called anaerobic digestion, where organic materials such as manure, crop residues, energy crops, and food processing residues are broken down by bacteria in the absence of oxygen. So the composition of biogas typically includes 50 to 60% methane, which is the primary component of natural gas, and then 35 to 40% carbon dioxide. Then biogas can be directly utilized as a fuel, for example, in an internal combustion engine to generate both power and heat, or that the biogas can be purified further to produce high quality methane for supplementing the natural gas. So this is known as biomethane. Then we have bioheat. So bioheat is generated by directly combusting or densifying biomass crops like switchgrass and miscanthus as an example, as well as agricultural crop residues, forestry products, and other organic materials. So these can be turned into chips, cubes, briquettes, pucks, and pellets for actually producing heat and power. One of the most common forms of bioheat is generated through biomass pellets. So these are widely used for heating residential buildings, commercial properties, and even greenhouses. With the fluctuation of natural gas and oil prices, many greenhouse growers are turning to biomass combustion systems. So these systems offer a more stable and potentially cheaper energy source, helping to reduce the operational costs. So interestingly, biomass combustion not only generates heat, but also produces carbon dioxide. So this carbon dioxide can be used to enhance plant growth in greenhouse gases, making biomass a dual purpose energy source in agriculture settings. So in this way, we are actually giving CO2 to the plants, and at the same time, we're providing heat. So it's like hitting two birds with one stone. So this is a very, very potential or interesting application of bioheat. All right. So now we move on about to talk about the growing products in the EU. So this slide will highlight the growth and potential of bioproducts in the EU, but of course, this also applies to the other parts of the world. So in the EU, the potential markets for bioproducts are extensive, including polymers, lubricants, solvents, adhesive, herbicides, and pharmaceuticals. So these markets represent areas where bioproducts can actually replace or supplement traditional products. The bioproducts have already made significant inroads into many of these markets, so their presence is growing as consumers and industries recognize the benefits of bio-based alternatives. So I'm sure if you noticed, a lot of products now a lot of companies try to tend towards more bio-based products, as this helps the consumer to be more conscious of the product that they're consuming. So this is a very good thing on both sides, which is why these products are actually growing right now. Also, due to the new products and technologies, so the innovation is driving the new products and technologies that enhance the performance, cost, and competitiveness and market share of bioproducts. So the ongoing innovation is crucial for maintaining momentum in the bioproduct sector. Also, for the renewable raw materials in Europe, there has been a strong focus on using renewable raw materials as industrial feedstock for manufacturing since the early 2000s. So this focus aligns with the broader goals of sustainability and also reducing the dependency on fossil resources. So in the bottom of the slide, you see the four major growth areas. So these are polymers, solvents, lubricants, and surfactants. So we'll be talking more in detail about each of them in the next slide. So let's start with polymers. So bio-based polymers or bioplastics are produced from plant or crop-based monomers. So these monomers are derived from renewable biological resources, making them a more sustainable alternative to traditional petrochemical-based polymers. So plastics that are made from the traditional method using fossil fuels. Despite being derived from different sources, the bio-based polymers often have identical chemical structures and properties to their petrochemical equivalents. So this similarity actually allows them to be used in many of the same applications as conventional plastics. So it's not a disadvantage that we produce it from different bio-based resources. In fact, the chemical structure most of the time is quite similar. So this is why the bioproducts or the biopolymers are very competitive. However, to actually compete more in the market, they need to have a lower price, or benefit from tax advantages, or receive government subsidies. So these factors are crucial in making the bio-based polymers a viable alternative to the conventional plastics in the global market, because even though the final product is similar to the normal plastics, the technologies to produce the bioplastics, it's still quite expensive compared to the conventional fossil fuel method. So this is why it's important that there are incentives provided to those who produce bioplastics. So let's talk about example of a bioplastic, since you might be wondering. So the first example that we'll talk about is polylactic acid. So polylactic acid is made from glucose through a fermentation process that converts the glucose into lactic acid. The lactic acid is then condensed into lactide and polymerized into PLA using a catalyst. This process is entirely bio-based, so this distinguishes it from the traditional polymers or the traditional plastics. There is currently no economically and competitive industrial petrochemical route to produce PLA, so this reinforces the uniqueness of PLA as a sustainable polymer option, as the only way to produce it is through this bio-based method. So what is PLA actually used for? So it has a range of textile applications, including clothing, fiber fill for bedding, industrial fabrics such as wall panels, carpet tiles, and non-wovens. So these applications highlight the versatility of PLA in different industries. Not only that, but PLA is actually used in packaging applications. So this includes the coated paper and the board for milk, fresh yogurt containers, bottles and jars of milk, juice, and food oils, candy wraps, compost bags, and even thermoformed containers for food and fast food. Not only that, but PLA can actually be blended with other polymers to create hybrid materials. So an example of this is BASF's EcoView, which is a product of a successful blend of 55% biodegradable polyester, EcoFlex, and 45% PLA. So this blend demonstrates the potential for actually creating new materials with enhanced properties by combining biopolymers with other substances. So this is an intrinsic application that BASF has implemented. So this slide illustrates the chemical structure of the polylactic acid, focusing on the molecular makeup. So without going into too much detail, I'll just like to talk quickly about the molecular structure. So on the right side, we see that the structure of the lactic acid, which is the building block of PLA. So lactic acid is a simple molecule with a hydroxyl group, which is an OH group, and a carboxyl group, which is a COOH group, a chiral carbon center, making it capable of existing in different forms. As for the PLA polymer structure, so the larger structures on the left represent the polymerized forms of lactic acid, which is the PLA. These polymers are made of repeating units of lactic acid linked together through ester bonds. So understanding the structure without going too much into detail of the chemistry behind it is important because the arrangement of these monomer units actually affects the physical properties of the polymer, such as its melting point, strength, biodegradability. So this structure versatility is one of the reasons why PLA is a very widely used biopolymer in various applications. So of course, the chemical structure is always important as it gives us an insight of how the material is going to be like. All right, now let's talk about another biopolymer, which is polyethylene. So polyethylene currently is produced exclusively through the catalyzed polymerization of ethylene from steam cracking, making it 100% petrochemical process. So the current polyethylene that we get is coming from fossil fuels. However, there's a potential for a more sustainable approach. So ethylene, which is the key building block for polyethylene, can be also produced from ethanol derived from glucose fermentation, which is a bio-based process. So the environmental and cost efficiency of this process depends largely on the choice of the feedstock. The environmental and cost efficiency, as I've said, depends on the large feedstock. As for the economic calculations, they suggest that deriving ethanol from sugarcane is actually more efficient than from corn or sugar beets. So given its large-scale sugarcane production, actually Brazil is an ideal location for the ethylene production, sugar-based ethylene production, making it a key player in the biopolymer industry. So the diagram at the bottom shows the catalytic dehydration reaction or process for converting the ethanol to ethylene, which is a crucial step in the bio-based polyethylene production. So the shift towards bio-based production could make polyethylene a much more sustainable material in the future than the current way, which is produced through petrochemical process. So now let's take a closer look at the process flow diagram for producing a polymer grade ethylene from ethanol, which is the bio-based process. So first you start with ethanol. So this ethanol is typically derived from the fermentation of sugars like glucose. Then we have evaporation in a furnace. So the ethanol is first evaporated and then heated in a furnace. The heating fluid in the furnace may be operating under adiabatic conditions, depending on the specific setup, of course. Then in the reaction stage, this ethanol undergoes the catalytic dehydration, which is the reaction I showed you before. This basically removes water from the ethanol to produce the raw ethylene gas. Then quenching happens where the hot reaction products are quenched, rapidly cooled with water. This helps to stop any further reactions and condenses the steam generated in the process. Then we have scrubbing, which is basically the raw ethylene is then scrubbed with aqueous sodium hydroxide to remove any acidic impurities, resulting in a cleaner or a more pure ethylene stream. Then we have drying after the scrubbing to remove any moisture from the gas. And finally, we have the distillation and stripping.
So the crude ethylene undergoes distillation and stripping, basically to separate it into pure polymer grade ethylene and to remove any contaminants that come along with it. So this is just a quick scheme to give you an idea of how the process is to produce biopolyethylene. And this diagram, we also see a lot of different examples of biopolymers and their production pathways. So on the left, we have the different feedstocks like sweet corn, sugarcane, switchgrass, and agricultural waste. These are the starting materials rich in carbohydrates, starch, sucrose, glucose, fructose, and cellulose. These act as the monomer precursors, where these feedstocks are produced to extract these monomer precursors that we want. For example, starch can be broken down into glucose, and cellulose can be broken down into its glucose monomers. The monomer precursors are further processed into the specific monomers that we want. So lactic acid is derived from glucose and can be polymerized into polylactic acid, which is PLA that we have been discussing, while succinic acid and FCDA acid can be used to produce other biopolymers like PBS, which is the polybutylene succinate, and PF, which is polyethylene furanate. So these monomers are then polymerized into the biopolymers. So as we say, the lactic acid, we can produce PLA, which can be used for disposable cups and cutlery, for example. And other examples can also be produce other polymers, which can be resulting in the final products as shown here on the right. So this is just to give you an idea of that there's a diverse range of ways that you can produce biopolymers. This is another example where here on the left, we have different feedstocks like pine tree, lemon peel, tulip, mint. So, I mean, this is very interesting as before we wouldn't have seen these materials to be used to actually produce plastic. So this is a very interesting where we can utilize different resources to actually produce the final polymers that we need in today's society. Here we even have further examples. So we can use plant-based sources like soybeans, sunflower, castor oil plant, palm tree. And at the end, we can have products that end up used in nylon or self-healing elastomers or epoxy resin. So these are all interesting applications of biopolymers. All right, so we have finished biopolymers and now we move on to different category, which are the solvents. So let's talk about the global consumption of solvents. So in 2005, the annual global consumption of solvents reached nearly 20 million tons. So this highlights their significant role in various industries. So how can solvents be classified? Well, they can be classified by the chemical structure, which helps in understanding their properties and applications. So the main categories include oxygenated solvents, hydrocarbon solvents, halogenated solvents, and miscellaneous solvents. Their industrial applications are, or the industrial solvents are essential in many sectors. So they're widely used in adhesives, paints, coatings, pharmaceuticals, inks, printing, and even semiconductor manufacturing, as well as metal cleaning. So this broad range of applications underscore their importance in both the consumer products and industrial processes. So the table on the slide provides a summary of the typical type of solvents within each solvent family. So the ones that I've mentioned before. For example, for the oxygenated solvents, the typical types include alcohols, ketones, esters, and glycol ethers. So biosolvents or solvent replacement derived from biological resources offer a significant advantage in reducing the environmentally polluting volatile organic compound emissions, so VOC in short. This makes them a much more sustainable option compared to traditional solvents. However, for biosolvents to compete effectively in the market, production costs need to be reduced. Currently, one of the main challenges is making these biosolvents competitive with their traditional petrochemical-based counterparts. So some examples of the bio-based solvents include methyl solate, which is the soy oil methyl ester. Then we have ethyl lactate, which is the fermentation-derived lactic acid reacted with ethanol. Then we have D-limonene, which is extracted from the citrus rinds. And then we have PHA, which is from the fermentation of sugars or lipids. Then we move on to the next product category, which is lubricants. So bio-based lubricants, often referred to as biolubricants, are produced from various vegetable oils. So these include unmodified vegetable oils. These are oils used in their natural state without any chemical alteration. We also have modified vegetable oils, where these oils undergo chemical modification to enhance their performance in specific applications. Then we also have synthetic esters from modified vegetable oils. However, it's important to note that in the industry, there is no universally accepted definition of bio-based lubricants. So this lack of standardization can lead to confusion often. For instance, the term bio-based lubricant often implies that the product is biodegradable, but this does not necessarily mean that it's entirely made from bio-based materials. So this ambiguity highlights the need for clearer definitions and standards in the industry to ensure that the biolubricants meet both the sustainability and performance criteria. So modern biolubricants are primarily made from rapeseed oil, sunflower oil, soybean oil, and animal fats. So these oils are good because they're sustainable. However, there's an issue is that they're prone to oxidation due to their polyunsaturated fatty acids, so such as linoleic acid and linolenic acid. So this has caused the biolubricants to have oxidation problems. There's also issues with the stability and competitiveness with this biolubricant. So a lot of research is actually being conducted to see how we can improve the quality of biolubricants to ensure that they are up to the market standard compared to the petrochemical counterparts. All right, so now let's transition to the third section of our presentation, which is the bio-based methods. So what are the different approaches to actually make these bio-based products? So the first method is that nature often produces the desired molecular structures, which can be isolated using physical methods without the need for chemical modifications. So this is a significant advantage as it simplifies the production process and reduces the need for harsh chemicals. So examples include polysaccharides, which are like cellulose, starch, alginate, pectin, agar, chitin, and inulin. We also have disaccharides such as sucrose and lactose. We also have other natural compounds, including triglycerides, natural rubber, gelatin, flavors, and so on. So the use of plant biotechnology is set to greatly expand the production of these organic chemicals directly from plants, which are increasingly being seen as the chemical plants of the future. So this shift represents a move towards more sustainable production methods that leverage the inherent capabilities of nature. So this is the first method. The second method in bio-based method is to involves a one-step chemical or biochemical modification of naturally produced structures. So this method still maintains the simplicity while allowing for the creation of a variety of useful compounds. So what are the examples? The examples include cellulose and starch derivatives, glucose and fructose, glycerol, fatty acids, ethanol, citric acid, glutamic acid, and lactic acid, which are produced by fermentation. Then we also have lactulose, lactylol, and lactobionic acid, which is produced by isomerization. So these are the second method to produce bioproducts. Then we have the third method, which involves chemical or biochemical modification of naturally produced structures through multiple steps to create organic compounds and materials. So this process allows for the production of more complex and more specialized compounds. So examples include ethanol, which can be converted to ethylene. We also have sorbitol and mannitol. So these sugar alcohols are produced by the hydrogenation of glucose and sucrose, respectively, and are widely used in the food and pharmaceutical industries. Then we also have vitamin C synthesis, which can be derived from glucose through several chemical steps, so demonstrating the ability to produce essential nutrients from simple sugars. Then we have fatty alcohols, which are derived from triglycerides, and these are important in the production of detergents and surfactants. Then finally, we have succinic acid, which can be derived from glucose or carbon dioxide, and this is used in the production of biodegradable plastics, resins, and other materials. So here at the bottom right, we have the molecular structure of vitamin C and succinic acid, just for your reference. Finally, the last method that we discussed is called the back to C1 chemistry approach. So this involves breaking down biomass into the smallest components, like synthetic gas or methane, through chemical or biochemical degradation. So once these small fragments are obtained, they are reassembled into more complex desired structures in a controlled manner. So this process typically involves, for example, like syngas generation. So we use biomass, coal, or natural gas is converted to syngas through processes like gasification or steam reforming. And then we have the next process, which is the Fischer-Tropsch process, which basically converts the syngas to form hydrocarbon chains, which can then be used to produce various chemicals and fuels. So this method is versatile actually because it allows us for the conversion of a wide range of feedstocks into viable products, making it a key strategy in both the chemical industry and bioeconomy. However, this is the most complicated as we need to go through a lot of processes to obtain products. So we need to have commercialized technologies to ensure that we can adopt this approach to produce the desired bio-based products. So with this, I'll move on to the conclusion of this lecture. So we'll start talking about three different areas that the bioeconomy presents a lot of advantages to. So first, in socioeconomic. So a diversified and stable bioeconomy strengthens the overall economy by promoting farm diversification and also developing new industries and products. So it enhances the economic opportunities for rural communities and also reduces the reliance on non-renewable fossil fuels. As in terms of the environment, bioproducts offer significant environmental advantages, including lower greenhouse gas emissions during the manufacturing compared to the petroleum-based products. They also contribute to the environmental safety through reduced toxicity and greater biodegradability, all while using renewable feedstocks sustainably. And then it also impacts health. So the health benefits the bioeconomy holds potential health benefits by enabling the production of affordable and medicinal drugs and vaccines. So it also opens the door for developing new drugs that might not be possible with the traditional sources. So these combined benefits underscore the importance of advancing the bioeconomy as a key component of a sustainable and resilient future. In closing, the bioeconomy fosters essential collaboration across agriculture, industry, and research to create sustainable solutions. So the supporting policies and initiatives are crucial for the bioeconomy's growth, ensuring that it can flourish and meet its potential. Not to mention, investing in research and public awareness can highlight the benefits of the bioeconomy. And lastly, embracing this holistic or comprehensive approach will pave the way for a more resilient and sustainable future. Together, these elements will underscore the importance of bioeconomy in shaping a more sustainable world. So with that, I've come to the end of this lecture, and we'll just go ahead and perform a quick exercise to refresh our knowledge on this topic. So without further ado, feel free to raise your hand if you'd like to answer this question or open up your microphone. So the first question is, what is the primary goal of the bioeconomy?
Okay, everybody has access to chat. You can write your answers into chat. There we go.
So we have four options. Is it to increase the fossil fuel consumption, or to reduce the agricultural production, or to create sustainable alternatives to fossil fuels, or to promote non-renewable resources? So what do you think the answer may be?
Abdulqader, are you able to read the
Yes.
answers?
Let me check. No, I cannot see the chat at the moment.
Oh, okay. Most of the answers coming in are C.
Okay, let me see. Yeah, now I can see the chat. All right. So yes, you are right. So the answer is to create sustainable alternatives to fossil fuels. So as we know, fossil fuels are a very, very crucial and important problem to address, and the bioeconomy is one of the approaches to do that. So great. So let's go on to the next question is, which of the following practices is promoted by the bioeconomy? So is it A, the linear economy, which is the take, make, dispose economy model? B, wasteful consumption? C, circular economy? Or D, the resource depletion? So feel free to leave your answers in the chat. Okay, we have C's, we have some A's coming in. Okay. We have a D, all right, interesting. Okay, so the answer is, let's look at the answer. So the answer is C, circular economy. So as we mentioned, that the bioeconomy is actually promotes a circular economy in nature. This is because we produce uh, bio-based products from plants, for example, and then the waste can be actually used in further products. So we're not disposing of the waste, but rather we're regenerating it and recycling it. So this shows how the bioeconomy can actually promote the circular economy, because it does not work like the linear economy, which is the take, make, dispose. So the bio-based products will not just be disposed, but they can actually be recycled or remanufactured to other useful products. So this is why the bioeconomy uh, practices the circular economy. Let's move on to the next question. So what is the challenge facing the bioeconomy? Is it A, making bio-based products cost competitive with conventional products, which are the products produced through, for example, the petrochemical way? B, lack of interest in sustainable products? C, crop residues? Or D, animal manure? Okay, we have some A, we have some B. Okay, I'll just wait one more minute to see who else would like to contribute their answer. Dr. Lambert, what do you think the answer could maybe?
On what I would think it would be,
Yeah, what do you think it would be?
I would put A.
All right, okay.
But I see
So
most of the students do say A too. There's a couple of
yeah,
there's a C and a couple of B's.
all right. So we can see. All right, so the answer is, let's take a look at the answer. So the answer is actually A. So making bio-based products cost competitive with conventional products. So as I've said in the lecture, bio-based products can be competitive in terms of their properties, like the normal conventional counterparts. However, the technologies to produce these bio-based products are currently still expensive compared to the already established petrochemical counterparts. So this is one of the challenges actually facing the bioeconomy, where the current industries are trying to find ways to commercialize the bio-based products in a more cost-effective manner. With that, let us move on to the next one. So what type of energy is often associated with the bioeconomy? So is it A, coal energy, so energy from coal? Or is it B, renewable energy from biological sources? Is it C, nuclear energy? Or finally D, natural gas? Okay, so we have some B's coming in the chat. Okay, so far everyone has said B. Okay, I'll just wait a few more seconds. Okay, so it seems that everyone is unanimous on this one. So yes, the answer is B. So one of the strengths of the bioeconomy is actually utilizing renewable energy from biological sources, which makes it very eco-friendly and very sustainable in the first place. So the answer is B. Lastly, we have the final question, which is which of the following best describes the term bio-based products? So is it A, products made from fossil fuels? Is it B, products made from renewable biological resources? C, products that are exclusively synthetic? Or D, products that are non-renewable? So it's quite similar to the previous question. You might already know this one, so let's see. Let's wait for the answers. So we have B's coming through. And if I'm not mistaken, I've shown you two definitions of bio-based products. So according to the US, USDA, and also according to the EU. All right, so the answers that are coming through are all B. So yes, the answer is actually B. So bio-based products are products made from renewable biological resources. So as we said, agriculture waste, food waste, plants, biomass, all these are renewable biological resources. So I hope you have enjoyed this little interaction. And right now the floor is open for Q&A. So if you have any questions, feel free to leave them in the chat.